The Sun, a big ball of hot plasma in the center of our solar system, a body where 1.3 million Earths can fit inside it, and it accounts for 99.86% of the mass of all the objects in our solar system. It is the life source of our planet, consistently fusing its hydrogen to provide us with heat and light that we need for Earth to be habitable. But our Sun is only one of roughly 250 billion stars in our galaxy, the Milky Way, with likely just as many planets, if not more. When discussing planetary habitability, we need to know what type of stars that are realistically suitable for the likelihood of having a habitable world that we could colonize in the future. I must also emphasize that the stars themselves are the primary topic of this video. The Sun is often known as an average-sized star, but as we'll discover, this is not necessarily the case. It is classified as a G2 main sequence star, but to know what this means, we need to observe other stars and understand the Harvard spectral classification system. Most stars can be classified into 7 main spectral types depending on the primary form of electromagnetic radiation being emitted. They are separated into types O, B, A, F, G, K, and M, with O being the hottest, bluest, and emitting primarily in the ultraviolet, and M being the coolest, most red, and emitting primarily in the infrared, with all the other types scaled in between this. A number between 0 and 9 will be assigned to the star depending on its surface temperature, with 0 being the hottest and 9 being the coolest. For example, a K0 will be hotter than a K1, but will be cooler than a G9. If the exact spectral type and assigned number is not known precisely, or if we want to give an approximation or generalization, then it's acceptable to use the terms early and late, where early represents hotter stars and late the cooler ones. Another spectral classification method, known as the Yerkes system, is used to organize stars into how luminous they are, as a general indicator for the size of the stars. They use Roman numerals to describe the class a star is in, with 0 being hypergiants, 1a being luminous supergiants, 1b normal supergiants, 2 bright giants, 3 normal giants, 4 subgiants, 5 main sequence stars, and 6 subdwarf stars. There is also a 7 for white dwarfs, but they have their own spectral classification scheme. So to complete a designation of a star, for example, an O21b will be a hot blue supergiant star, a G74 will be a cool yellow subgiant star, etc., etc. It is important to note that 90% of all stars are main sequence stars, including the Sun, and that stars can change spectral and luminosity types over time depending on their evolutionary path. Our Sun, for example, will transition into a late M-type normal giant once its hydrogen supply starts to deplete. Now that we know the basics of how stars are classified, we can now discuss which types of stars have the potential to be habitable for us. For starters, we can rule out all supergiant, giant, and subgiant stars. Though they may be fascinating to look at, they are too large, too variable, some even pulsating, and are not stable for a long enough period of time. It is also unlikely that planets can even form around these stars, as the strong stellar winds could blast the protoplanetary accretion disk away, and as to date from what we've discovered, the only way there could be planets orbiting giant stars is if the star was once a main sequence star. Compact stars, better known as stellar remnants, such as white dwarfs, neutron stars, and that includes pulsars and magnetars, and black holes, though popular in science fiction, can also be ruled out. These form after the red giant phase of a star, when a nova or supernova event occurs. The aforementioned objects are the result of this event, and it depends on the mass of the progenitor star for which one of these forms. Low mass giants will form white dwarfs. Anything between 10 and 29 solar masses will form a neutron star, and stars more massive than that, usually the luminous supergiants and hypergiants, will form a black hole. Though planets have been known to orbit at white dwarfs and neutron stars, they are simply too small, don't emit enough right radiation, and don't emit enough heat for a planet to be habitable. In the case of neutron stars, especially pulsars, they can emit high-intensity X-rays and gamma rays which instantly kill biological life forms as we know them on planets orbiting them. The atmospheres of the planets would also be stripped off and ionized, and all of that can be applied to magnetars as well. Stellar mass black holes are arguably even worse, as there is no light directly emitted from them at all. The only possible source of heat will be from tidal forces. Supermassive black holes in the realms of millions of solar masses are also a definite no, so you won't find a real system like the one in the movie Interstellar. A possible planet would be ripped apart by tidal forces before it became anywhere close to being habitable. Subdwarfs, both hot and cool, have their own problems too. Hot subdwarfs are essentially larger versions of white dwarfs, but instead of losing its hydrogen outer layers to a nova event, interactions with a binary star have shedded most of it off, resulting in the star mainly consisting of helium. However, it is not as compressed and is continuing to fuse, unlike a white dwarf. They're about the same size as small M-type stars, but temperatures that put them into spectral types B and O. The problem for them is that as they lost most of their mass, the systems they originally had would become significantly unstable, either ejected completely from the system or collided with the subdwarf itself. New planets, such as the ones possibly orbiting Kepler-70, would form from the remnants of the mass shedding. They would be far too close to their stars, with temperatures exceeding 5,000 Kelvin, evidently scorched and without question will be uninhabitable. Cool subdwarfs are not related to hot subdwarfs other than their size. They often have low metallicities, a lesser concentration of heavier elements than most other stars. This changes the mechanics of how the star works, so it will be hotter and smaller, but not as luminous. Cap-T star is an example of one, being only 12.76 light-years away, having a solar mass of 0.274 and a temperature of 3,550 Kelvin, which is much hotter than main sequence stars with a similar mass, but only a luminosity of 1.12% that of the Sun. This means that cool subdwarfs barely radiate their energy into space, so possible planets will receive very little energy from their star. That and the added problems that M-type stars face, which will be discussed later, mean that the potential candidates around orbiting these stars should be ruled out. With the non-main sequence out of the way, let's go through each of the spectral types for the main sequence. Spectral type O stars are very rare. Only one in roughly 3 million stars are of this type. They have similar problems to giant stars, as that is what they are in their own right. They have a solar mass of at least 15 and have a temperature of excess of 30,000 Kelvin. They are often only found in stellar nurseries. Like I previously mentioned, most of the radiated output of the star is in the ultraviolet, and henceforth a deep blue in colour. The sheer intensity of the star's output means that they burn through most of its hydrogen fuel within a few million years of its formation, and will go supernova long before any potential planets can even form, let alone have a habitable planet. These types of stars are a danger to neighbouring systems, as the radiation, or more specifically, the gamma-ray burst from their supernovae, can cause serious damaging effects on the atmospheres of planets, and if close enough can strip it off entirely. On Earth, it is thought that one of the possible causes of the Ordovician Solarium mass extinction, 443.8 million years ago, was caused by a gamma-ray burst, depleting a portion of the ozone layer and making the organisms of the shallow seas very vulnerable to ultraviolet radiation from the sun, which resulted in 85% of marine species being wiped out. So far, planets have not been detected orbiting O-type stars, but smaller neighbours that have one of these stars in their backyard are unlikely to host planetary candidates for the reasons given. B-type stars in general are somewhat similar to O-type stars, still shining with a blue colour, but they have between 2 and 16 solar masses, with temperatures between 10,000 and 30,000 Kelvin. They are more common than O-type stars, but they are still considered to be very rare, with 1 in 800 stars being of this type. Because they don't burn their hydrogen as ferociously as them, they do live for longer, and this will be the continuing trend as we look at the other spectral types. But for B-type stars, they don't live much longer, in a period of a few tens of millions of years, again depending on their mass and temperature. These are also often found in stellar nurseries, and don't live long enough to drift away from the region they originated. To put The timescale of these stars lies into perspective. If our Sun was a B-type star, it would have died and went nova long before our Moon would even form, which is not enough time for a planet to cool down from its formation and become habitable. Planets have been detected orbiting some of these stars, however it's debated whether these objects are too large to be planets. The habitable zone of a small B9 main sequence star would extend to the orbit of Uranus, which is too far away for a terrestrial or silica-rich planet to form. A-type stars have solar masses between 1.4 and 2.1, with surface temperatures between 7,600 and 10,000 Kelvin. They shine with a white color, with some early A-type stars having a bluish tint to them. 1 in 160 of these stars are of this type. They typically last a few hundred million years before evolving into red giants. Late A-type stars such as Altair are over 1 billion years old, but it is unlikely for such a star to live longer than 1.5 billion years. On Earth, life did form within this time frame. However, it was single-cell life, in an atmosphere primarily dominated by CO2 and nitrogen, which are mainly the gases generated from volcanism and asteroid impacts, especially during the late heavy bombardment. If we were to find a planet with similar conditions to this orbiting such a star, it would still be uninhabitable for us. Another problem is the light they generate is still primarily in the ultraviolet and blue end of the spectrum. The lack of red light means that Earth-like plant growth will be inhibited, affecting crop yields and forcing us to rely on methods such as hydroponics for growing food. Getting an artificial ecosystem going with Earth-based life forms trying to adapt to the conditions is essentially a challenge not worth the effort. Even on Earth, us humans and many other life forms have problems dealing with ultraviolet rays from our Sun. So you can see the trouble with a star with a far greater output. Even that in the extreme ultraviolet would have on a planet despite the orbital distance. Speaking of distance, the habitable zone for an A9 star will be in the region of the asteroid belt and the orbit of Ceres. This is close enough for an Earth-sized terrestrial planet to form, but from what we've currently discovered, only one possibly terrestrial planet has been discovered orbiting an A-type star, Kepler 1115b, a super-Earth with a 23-day orbit, so it is evidently scorched and uninhabitable. F-type stars have solar masses between 1 and 1.4, with surface temperatures between 6,000 and 7,600 Kelvin, shining with the colors pale yellow to white. 1 in 33 of stars are type F. It typically lasts for periods of between 2 and 5 billion years, depending on their mass and temperature. They do drift far enough away from stellar nurseries to be away from the dangerous supernovae, unlike the previous classes. Early F-type stars have similar problems to that of A-types, being too hot, too intense with the light intensity, and not living long enough. But late F-type stars that live for at least 3 billion years are promising. The reason for this figure is all to do with oxygen. Like I explained with A-type stars, early Earth had no free oxygen in its atmosphere. In fact, for nearly half of Earth's history, there still was no oxygen in its atmosphere. It took until roughly 2.4 billion years ago, when the Great Oxygenation Event occurred, from the emergence of photosynthetic organisms known as cyanobacteria, the very distant ancestors of modern plants. Even after this, Earth's atmosphere then would still be toxic to us, as it would take roughly another 1.5 billion years for the oxygen to be fully absorbed into what is known as oxygen sinks, which was first the oceans through the reaction of dissolved minerals such as iron, and then through the weathering of rocks on land. Only after that did the concentration of oxygen in the atmosphere begin to significantly increase. In short, the process to get a breathable atmosphere took 4 billion years. Perhaps conditions on a potentially habitable planet with life orbiting a late F-type star could allow for this process to accelerate, but life as we know it only had one genesis, so there is no way to know for sure yet. Atmospheric oxygen can also form abiotically, but unlikely for the concentration necessary for it to be breathable, either not enough or even too much, as that is also deadly in its own different way. The habitable zone for a late F-type star will be within the orbits of Mars and the inner part of the asteroid belt. From looking at the NASA Exoplanet Archive, for F-type stars there have been over 250 potentially terrestrial planets currently discovered, primarily super-Earths, but includes many Earth-sized planets too. Almost all of them are orbiting mid to late F-type stars. None of them, however, are in the habitable zone, but their presence shows that they are possible and mean that F-type stars are potential candidates for habitable planets. G-type stars are by far the most well known. Primarily, as I already stated earlier in the video, the Sun belongs to this group. They have solar masses from 0.84 to 1.15, and a surface temperature between 5,300 Kelvin and 6,000 Kelvin, showing with yellow to white, and 1 in 13 of stars being of this type. Unless the meaning of the term average star refers to the fact that it is in the main sequence, these stars, including our Sun, are in the top 12% of hottest and brightest stars, which is hardly average. They last a long time, roughly 10 billion years, with late G-type stars lasting a few billion years more, which is more than enough time for a habitable world to form, as Earth has proven. Over 600 likely terrestrial planets have been discovered so far orbiting G-type stars, but only 2 of them are in the habitable zone. Also, when I mean habitable zone, I'm referring to the conservative habitable zone as opposed to the optimistic habitable zone, where the scale is much more fine and where the conditions are far more likely to be habitable than the latter. The planets in question are Kepler 452b and Kepler 1638b. There are a couple of others including KOI 4878.01, but they have yet to be confirmed to exist. The range of the habitable zone for stars like these are from the orbits of Earth to that of Mars on the outer edge. Despite looking like our natural targets to look for, and would be the easiest to adapt to if it was similar to our Sun, the problem is that this isn't the case. Our Sun is very quiet in terms of its overall variability when compared to that of other G-type stars. The bottom graph here is of KIC 7849521. It is typical of what you see for variability, with more star spots and dangerous flares and coronal mass ejections. Our Sun, as you can see, is not like this, and there is evidence that it has been the same as it has been for at least the last 9,000 years. Very likely much longer in the realms of hundreds of millions of years, given that there's no evidence for the Sun being directly involved with any of the big mass extinction events. So this means that planets orbiting most other G-stars will more likely experience frequent climatic changes as a result of the activity from them. So this is something to consider when looking for habitable planets orbiting these stars. But overall, it still means that these are good stars to look for when trying to find habitable candidates. I am now going to disrupt the order for a moment and now mention M-type stars, more often known to us as red dwarfs. The reasons will be clear for this once I explain the details about them. They are by far the most abundant of stars, with 3/4 of all stars being of this type. They generally have solar masses from roughly 0.08 to roughly 0.6, and a temperature of roughly 2000 Kelvin to 3900 Kelvin, meaning they shine red. Because of the convective nature of these stars, they can live for trillions of years. The habitable zone for all but the largest of red dwarfs is within 0.1 astronomical units, well within the orbit of Mercury. You will often hear in the media, and sometimes the scientific literature, occasionally mentioning the discovery of an Earth-like planet from time to time orbiting these stars, but there are a significant amount of challenges. One such challenge is the most obvious one. The small size means that the electromagnetic radiation it generates is primarily in the red part of the spectrum and infrared. This is the opposite to the problems which I was describing with A-type stars. Not enough visible and blue light means that Earth-like plants using photosynthesis cannot grow properly and effectively, so making an artificial ecosystem will be difficult here. Another problem is that of tidal locking. Because the habitable zone being so close to the parent star, potentially habitable planets are dominated by the tidal forces of it. This means that its initial rotation speed from its formation changes to be in sync with its orbit, resulting in one side of the planet constantly facing the star and the other side never seeing it, so there are extreme hot and cold sides to the planet. It is possible that atmospheric circulation could mitigate this somewhat, or at the very least, the twilight zone, a thin region on the planet between both extremes, could be habitable. It is not just tidal locking, but also tidal heating that should be a concern. The most famous case is that of Jupiter's moon Io, which is close enough for it to heat the core and drive active volcanism. The same process can occur for these planets, resulting in Venus-like hothouse conditions and rendering them uninhabitable. If all that was not already bad enough, the variability, the changes in the star's luminosity over time, is often chaotic and extreme for M-type stars. Like I previously described, these stars are convective in nature, so they have very strong magnetic fields, which then cause them to have very powerful flares and coronal mass injections on a regular basis. That causes the luminosity to jump to several tens, hundreds, even thousands of times out of normal levels. Many of these deadly flares are emitted as far ultraviolet, extreme ultraviolet, or even as X-rays, so a possible habitable planet will be very close to these events, being in the firing line to them. Without a very strong magnetic field of their own, hundreds of times stronger than that of Earth's, these flares would eventually erode the atmosphere of these planets and could be very harmful to life, also rendering them uninhabitable. As a red dwarf ages, its overall activity decreases, but they are still deadly and the damage would have already been done at this point. Despite possible habitable planets orbiting these stars, such as the ones around Gliese 581, TRAPPIST-1, and Proxima Centauri being very popular with the public and astronomers alike, recent research has shown that these stars are terrible candidates for habitability for all the aforementioned reasons. There have been around 180 terrestrial planets discovered so far orbiting these stars, with 14 being in the conservative habitable zone. But as we just discussed, just being in the habitable zone does not necessarily mean it is likely of being habitable, as you have to take other factors into account. There is a very good video by Launchpad Astronomy that goes into further details about the issues surrounding M-class stars, which I've linked above if you're interested. There is also an extension to the Harvard spectral system that involves objects that are cooler than M-type stars. 3 more spectral types for objects below 2000 Kelvin, with masses between 13 and 80 times that of Jupiter, types L, T, and Y. Almost all objects that belong to these spectral classes are known as brown dwarfs, which are stellar bodies that do not have enough mass to support hydrogen fusion in their cores, and as a result are not stars, with Class L being the closest to stars, and Class Y being closest to gas giants. On some occasions there can be L-class stars and M-class brown dwarfs, but the main difference between them is the mass. Like I said, they simply do not have enough of it to sustain hydrogen fusion. As they don't emit enough energy, planets orbiting these objects are likely to be uninhabitable, with the problems of tidal locking and heating also being prevalent. The coolest of brown dwarfs, type Y, can be even colder than Earth is, so there is no point discussing the objects known as sub-brown dwarfs, objects with less than 13 Jupiter masses, as you can see the problems that arise. And before showing K-type stars, I'd like to show you this diagram that shows the differences between the convection models of stars and explains why massive stars die so fast and why small ones live for a very long time. In massive stars, they follow a method of nuclear fusion known as the carbon-nitrogen-oxygen cycle, or CNO for short. It is a catalytic cycle, starting with a carbon-12 atom encountering a hydrogen atom under intense pressure and temperature. This reaction then forms gamma rays and an isotope of nitrogen, nitrogen-13, which then quickly decays into neutrinos and positrons and an isotope of carbon, carbon-13. That, meeting another hydrogen atom, forms nitrogen-14, or simply a nitrogen atom, and some more gamma rays, which then reacts with another hydrogen atom, forming an isotope of oxygen, oxygen-15, and more gamma rays. That then quickly decays into neutrinos and positrons, and nitrogen-15. When that finally reacts with another hydrogen atom, you get helium and a carbon-12 atom, and then the process starts all over again. This results in the larger stars burning the hydrogen fuel far more intensely. The energy released exits the star rather quickly, radiating into space and therefore giving a high surface temperature, appearing blue. Stars less than 1.3 solar masses primarily follow a different method of nuclear fusion, known as the proton-proton chain reaction. This is where hydrogen atoms on their own fuse into deuterium, where one of the atoms is neutralized, loses a positron and forms neutrinos. Another hydrogen atom comes and reacts with the deuterium, forming gamma rays and helium-3. Then this isotope of helium fuses with another one of itself, forming a normal helium atom and two hydrogen atoms. This is the reaction that produces the most energy and generating the star's light. In stars with a similar size to our own Sun, shown by the middle diagram, the radiative zone of where the proton-proton reaction is in the core of the star, where most of the energy is generated, but it is surrounded by a convection zone. Helium atoms generated can get caught in this convection zone instead of instantly accumulating in the core, as is the case for larger stars. It can take tens of thousands of years for energy to escape from this zone into space. The size of the convection zone varies depending on the mass of the star. More massive stars, such as F-type stars, have a larger radiative zone and small convection zone, and lesser massive ones, such as K-type stars, have larger convection zones when compared to their radiative zones. Stars with solar masses less than 0.35 have the entire star as one huge convection zone, excluding the core, which itself is a separate convection zone. This means that the helium generated will never accumulate in the core and the rate of hydrogen fusion is low, hence the lower temperature and why they live for trillions of years. It is important to note that this should be thought of as a scale, not a model. Stars on the other side of it tend to have a larger proportion of themselves as the CNO convection cycle the more massive they become. From smallest to largest, it goes convective dominant, to convective outer layer and radiative inner layer, to radiative outer layer and CNO convective inner layer. And for reference, our Sun does have the CNO cycle in it, but it is a very minor component for its energy generation, only 1.7% being of this. So now that we know the basics of how the interiors of stars work, this leads us back to K-type stars. They have solar masses between 0.5 and 0.85, with temperatures between 3900 Kelvin and 5300 Kelvin, resulting in them shining orange. The last 12% of stars belong in this category, with 1 in 8 being a K-type star. Depending on their mass, they are projected to live between 20 and 70 billion years, meaning not a single main sequence star in the universe of this type has died of old age. This is plenty of time for life to possibly develop if they are, of course, not positioned in a dangerous area of the galaxy. Habitable zone planets orbit far enough away, roughly 0.3 to 1.3 astronomical units, which avoids the possibility of tidal locking, and the threat from powerful flares is also diminished because of this. The convective dominance that M stars had is not as prevalent with K-type stars, and as a result they are much quieter, but it still could be a prominent problem for late K-type stars. The light they generate is enough to satisfy Earth-like plants of photosynthesis, and the harmful effects of ultraviolet light will be lessened as the stars don't generate as much. Another thing I've yet to talk about is the probability of Earth-sized worlds being developed. The chance of this happening is much greater orbiting smaller stars than our Sun, as there is often less material in the protoplanetary disk for large Jupiter-sized planets to form. But this is a general trend, it is not a certainty for every star. Currently, there are over 450 possible terrestrial planets orbiting main sequence K-type stars, with 15 of them being in the optimistic habitable zone, and 2 of those within the conservative habitable zone. Those planets being Kepler 442b and Kepler 62f. Out of the 2 of them, Kepler 62f looks like the most promising candidate, with an Earth radius of 1.41, a mass of 2.8, and a density of 5.49 grams per cubic centimeter, which is almost the same as Earth's. The only possible flaws for this planet could be the equilibrium temperature, which is minus 65 degrees Celsius, which is rather chilly, but this can be rectified if the planet has a thick atmosphere of greenhouse gases. For reference, the equilibrium temperature for Earth is minus 18 degrees Celsius, and it is the atmosphere and its contents that drive it to an average of 14.6 degrees Celsius. We also, of course, don't have the technology yet to know the atmospheric composition of this planet. It is likely rocky, but it could have a toxic Venusian atmosphere, or it could have no atmosphere at all. Or the atmospheric pressures could be okay, but it could consist entirely of a compound like methane or ammonia or CO2. We simply don't know. Though not every star in this category would be perfect, these are far the best type of stars to look for when searching for habitable planets, and they are often referred to as Goldilocks stars. 2 of the 15 planets within the optimistic habitable zone are within 50 light-years of us, those being HD 40307G and HD 219134G. Both of them are likely too massive for us to consider colonizing in the future, likely both to be mini-Neptunes. So one of the main setbacks so far for these stars is that we have not detected any good candidates that are near us, as the aforementioned Kepler objects are often hundreds of light-years away. Kepler 62f, for example, is at a distance of 1,200 light-years. It is also the primary reason why many people are simply not aware that these are the best stars to look for, as most of the well-known objects like TRAPPIST-1 and Proxima Centauri are very close to us in terms of interstellar distances, and it is generally harder to detect Earth-sized planets orbiting these K-type stars rather than M stars, due to them being more luminous and less affected by the gravity of the planets, so it is more difficult when using the transit and radial velocity methods. So to conclude, most stars in the universe will be very hostile to life and ourselves. Stars much larger and much smaller than our own Sun have their own set of significant problems that makes possibly living around them a very difficult challenge to overcome. The most ideal stars for us to look for are mid to late F-type stars, G-type stars, and especially K-type stars, but the conditions necessary for habitability are very fine indeed. A star too variable could cause climate chaos and atmospheric erosion. A planet too big could result in being like Venus or Neptune. A gamma-ray burst early in its history could ruin a solar system permanently. You have to think of every possible parameter from our current astronomical understanding before you can proclaim it Earth 2.0. Coming to conclusions before having all the information is not good science, and will only lead to confusion, disillusionment, and even ignorance down the line. It also makes you think about the very slim probability for everything to go right for us to exist on this planet. While it will be amazing to find a planet like ours, we don't know if we ever will find one within our lifetimes, if ever at all, which means we should still cherish our own, but still never stop looking. There are many more factors and impactors in the universe that can affect a star's ability to host habitable planets, such as the effect of binary stars and the metallicity of the star, which I have yet to talk about in detail. There will be topics on future videos on planetary habitability. Here is where I'll end the video for today. Hopefully it has given you a better understanding of the stars that surround us, and which ones are the ones to look for when you want to find potentially habitable planets. So if you're still here, thanks for your time. The next video will be on the configuration of other solar systems, and how they can affect the habitability of planets. If you think you have found an error in my videos, then please don't hesitate to comment and to correct them. I have also never made a video as complex as this. Trying to condense so much information about all the main types of stars and their relation to habitable planets into a somewhat simplistic form was a challenge in itself, so any feedback on the structure of the video will be appreciated. Thanks again, and goodbye.